this is an IR spectrum. It could be responsible for either of these molecules there. So what we're going to do, we're going to match each spectrum with the structure of the entries. So let's find out how we're going to do that. These are IR spectrum given. So you need to start picking out what is a characteristic signal that you can use to solve these things out. So I say there's some sharp band there, right? That's definitely identifiable. These are 3,000 lines right here. 3,000 lines right there. And then there is most of the signals are a little below that. That only means that it's saturated carbon hydrogen. You got nothing showing up a little above, then you may not have bubble bonds. Yes. But what else is really pinpointing this one? That reason, that's a 2100. You don't normally see anything there unless you got something with a triple bond, right? 2100 is a typical for the carbon triple bonds. If it's a carbon nitrogen triple bonds, it could be a little higher. So I wouldn't exclude the possibility of carbon nitrogen triple bonds, but you don't see any of the nitrile, which is the carbon nitrogen triple bonds, in that example. So that means that these might be triple bonds. If that's a triple bond, this makes sense. If the triple bond has a hydrogen like this, then these signals is going to show there. But if this signal is there without that, then that cannot be the triple bond with hydrogen, right? It has to have both. And an example definitely have both the triple bond and then the half carbon hydrogen bond. That is responsible, this one and that one. And then you got no carbonyl, nothing there. All of the other molecules has a carbonyl. So there's a 1700 reasons, right? That's a 1700, you got nothing there. So that has to be this. So it's kind of you to narrow things down. Oops. That's basically, oops, sorry. That's basically what is talked about. And that's triple bond there, and then you got no carbonyl. So that, I think, none of these four, but only this one can make this IR spectrum. So I think that's probably the simple one. And the next one, okay, let's find out what are the characteristic ones. You got strong band, that's about 1720. So that's very typical carbonyl, either ketones, aldehyde, carboxylic acid, but not ester, not amide, right? If it's a carboxylic acid, then you see a very broad OHP, which is not there. So this is not a carboxylic acid, and the example doesn't have carboxylic acid either. What you have here is you got B signal right there. That's a very characteristic. Normally you don't have a no absorption there, but this one, that's a 2800. Once you hear that number, you should remember, oh, this might be the number, right? Along with the carbonyl signal. So those is very characteristic. This one, along with this, is showing that yes, this must be the number. And then now the signals right there. And then I want to point out some other things might be useful. For instance, there is a very small short band right there, 1600. As I said, it's not the strongest band, so you may be able to miss it or something else with overlapping the regions. But if it shows up, the 1600 is like the stretching signal of the benzene. So if you see this peak at 1600, I mean, of course, this is a benzene, that is a benzene, this one is a benzene. So all three will show this band, maybe overlapping with others, but if you see it, that is kind of indicating that you may have a benzene in the molecule, and it is benzene there, which is aldehyde signal. Right? But the question is, what is that one? That's happening around what 3400. I mean, 3400 is close to 3300. That's where NH peak shows up, OH signal shows up, and there could be carbon triple bond hydrogen signal. But if that's the one, it should be much more sharper. So I don't think that's a possibility there. But I mean, it might not be that because OH is typically more broad and then more intense. That's kind of small. So do you think that must be the name? I mean, that's an amine signal. It could be as small as that. I mean, it could be big, just like what we saw before, but it could be as small as that. So that signal is kind of a leading you to think that the molecule may have an amine there, but none of these molecules has an amine. So how would that happen? Why these signals showing up? So when you see this 3400 signal, this is something you got to be careful. I don't know if you have played any musical instrument, but there's something called the harmonics, right? Overtones. Especially when you have really strong, loud notes you're playing, the harmonics always showing up. And which one is a loud signal there? This one. 1720, this is the biggest band, and then that's kind of a really intense signal right there. And then the overtone is a kind of twice the frequency by shorting the wavelength half. And that must be double the frequency up. That always show up when you plug in the guitar string. The harmonics always goes together because that's kind of wave properties. So 1720, the first harmonic must be double the number as a frequencies, which is a 38, 34. That's a harmonic of this signal. This is not an amine. So don't get fooled by that. If you have a really strong coordinate signal, there could be harmonic showing up 3400. So don't get fooled by that, because if you think this is kind of a real, then you're going to look for the amine, and maybe it's the example there was some amine there, that you're probably going to choose that one, and then that's a wrong answer. So you got to be careful reading that. So that's one of the things I'm pointing out. But this is the one that you really have to look into. All right, so what we have here, almost nothing there, and then there's a 3000 line, right? 3000 line, you got some bands a little above, so what that means is that you may have some double bonds. But there's a lot of double bonds here, so I don't know what it is, but double bonds are there. And then there's no signal there, there's not aldehyde, no triple bonds, and then suddenly you got signals here like a 1700. So 1700, what should we have to think about it? I mean, I told you that the covalent stretching can go down to like a 1680 by having a double bond conjugated to the covalent. Is this a conjugated ketone? I mean, that number is a little higher than that, right? I mean, you cannot completely eliminate the possibility this may be conjugated ketone, but still, the typical number, we should see the band below 700, like a 1690, 1680. But 1700, that could be easily mistaken by the regular ketones too. So I don't know, I mean, that number is kind of confusing, right? That's the thing. And then, so let's start looking at, what this point out is we have a carbonyl there, and this molecule has a carbonyl. Whatever the carbonyl is, it is there. So it cannot be this one, because that one doesn't have a carbonyl. It could be either this, that, this. It's a full possibility. So we have to figure out what will be the carbonyl structure signal for each molecule and try to match with this one. All right, the first example is a conjugated. But there's a carbonyl here, but double bonds is conjugated to that, when conjugated next to that. So this is a carbonyl, going for the wrong directions. This is a carbonyl that is gonna make a resonance structures. So this is what we talked about, conjugated ketone, that it goes down about 30. So it becomes like a 1690, 1680. I think that's a little too, this is lower than what we see here. I don't think that's that one. And then besides, there's another evidence you can potentially use. As I said, the 1600, that's a signal right there, right? This is that sharp band, 1600. That it could be coming from the benzene. So the molecule has a benzene, and this one doesn't have a benzene. So not only this carbonyl will show the lower frequencies, but also there's no absence of benzene. Sounds like this may not be the choice. But what about the other three? That one is an aldehyde. If this is the one that we should see the 2800 signal, which is not there, so cannot be that one. So this is a big split out because there's no carbonyl here. So we got three things that it's eliminated. But now these two, which one of these two will be that. That's an aster, right? If it's an aster, it's going to be higher than 1710. It could be pushing to the 1730, 1740. It could even get higher than 1750. That's 1700. So it cannot be this one. But if you look at the other one, that is also aster. So we got nothing responsible for this spectrum here. I mean, that's the most likely what you guys think. But this is what makes things complicated and what you need to figure out. This carbonyl have a benzene next to it. What that means is this looks like a conjugated carbonyl right there, right? So they can make a resonance structure. It's a minor contributor, but if they make a resonance structures, because the unsaturations of my next step carbonyl of an aster, it's going to be shifted down. But think about this way. Aster typically showing like a 1720, 1730, but it's shifted down because of the conjugation about 20 to 30. Then that's going to make it like a 1700. So by the look at the position of the 1700, it looks like a conjugated ketone or the regular ketones, but it is actually conjugated aster. So you got to think about these possibilities when you look at the provenance signal and find out what it is. But not because nothing else can make this carbonyl go down to 1700. We have to accept the fact that this must be this one. It's benzene conjugated, aster will make the signal goes down to 1700. So this is how the structure changed the signal. These are kind of things that we're going to ask in the test. Now let's think about like what we have to do. So you got to be looking at what else can complicate the issue. Anyway, so this is what I really want to do with you, because of conjugation, what's next to those, each function of which, it changes the number, it moves it around. And that's what you need to pay attention to. All right, the next one is pretty simple, because the next one, you got nothing except the carbonyl showing up. That number is really high, like 1760, I believe, 1760. This is a pretty high number for the carbonyl stretching signal. That belong to the aster. So these ones are definitely aster. Right. Regular asters like this. And these asters, don't choose this one for that, because that carbonyl, as we talked about, is conjugated to the benzene, will bring the frequency down. So only aster without any conjugation is this one. That's the only one. And then we have a benzene there. You do the 1600 sharp stretching signal there. That's typical to benzene. That's why you should see that kind of showing that you have benzene there.